Welcome to today's session. In this video, we'll tackle LeetCode problem number 522, longest uncommon subsequence 2. This problem is a fascinating exploration of string manipulation and uniqueness in arrays. We'll walk through the problem statement, break it down, and explore efficient approaches to solve it. Let's get started. In this problem, we are tasked with finding the length of the longest uncommon subsequence from an array of strings called strs. If no such uncommon subsequence exists, we return -1. Now, a subsequence is formed by deleting some characters, possibly none, from a string without changing the order of the remaining characters. For example, from the string ABC, we can form subsequences like ABC, or even an empty string. An uncommon subsequence, on the other hand, is a subsequence of one string that is not a subsequence of any other string in the array. The input is an array of strings, where each string consists of lowercase English letters, and the length of these strings and the array size fall within the given constraints. The output is a single integer, representing the length of the longest uncommon subsequence, or -1 if no such subsequence exists. Let's look at an example where the input is ABA, CDC, EA. Here, all three strings are distinct and none of them is a subsequence of any other string. For instance, ABA is not a subsequence of CDC or EAE, and the same holds true for the other strings. Since each string is both unique and its own longest uncommon subsequence, the result is the length of the longest string, which is 3. On the other hand, consider the input, AAA, AAA, AA. In this case, all strings are subsequences of each other. For example, AA is a subsequence of AAA, and all instances of AAA are identical. As a result, there is no uncommon subsequence, and we return -1. Now, consider the input, A, B, C. Each string here is distinct, and no string is a subsequence of another. For example, A is not a subsequence of B or C, and the same applies to the other two strings. Since each string is its own uncommon subsequence, the length of the longest uncommon subsequence is simply the length of any string, which is 1 in this case. These examples highlight how the problem is solved by identifying the strings that are not subsequences of others, and then determining the maximum length among them. There are some important constraints and edge cases to consider. First, the number of strings in the array can range from 2 to 50, and each string can have a length between 1 and 10. All strings consist only of lowercase English letters. One edge case arises when all strings are identical. In this situation, no uncommon subsequence exists, and the result is -1. Another scenario is when all strings are distinct and none is a subsequence of another, where the output will be the length of the longest string. Duplicate strings also need special attention, as a string cannot be an uncommon subsequence of itself. Finally, strings of varying lengths must be checked carefully, since a shorter string can still be a subsequence of a longer string. The key observation is that a string can only qualify as an uncommon subsequence if it is not a subsequence of any other string in the array. The longest such string determines the final output. To solve problem number 522, the goal is to determine the length of the longest string in the array that is not a subsequence of any other string. Let's break this down. A subsequence is formed by deleting some or no characters from a string while maintaining the relative order of the remaining characters. An uncommon subsequence, on the other hand, is a string that does not appear as a subsequence in any other string in the array. One straightforward approach to tackle this problem is the brute force method. Here, for each string in the array, we check if it is a subsequence of all other strings. If it isn't, that string becomes a candidate for the longest uncommon subsequence. Finally, we return the length of the longest such string, or -1 if no valid string exists. While this approach is intuitive and easy to understand, it does involve considerable computational effort, as we'll see shortly. The brute force approach involves checking if each string is a subsequence of all other strings, which is computationally expensive. To analyze its complexity, verifying whether one string is a subsequence of another takes L time, where L represents the length of the longer string. Since we need to compare each string with every other string, the total number of comparisons becomes n squared, where n is the number of strings. Combining these factors, the overall time complexity is n squared *L. This can become prohibitive for large inputs, especially if the strings are long. To address this inefficiency, we can leverage an optimized approach that utilizes sorting and filtering. The key insight here is that longer strings have a lower likelihood of being subsequences of other strings, which gives us a way to prioritize our checks and reduce unnecessary comparisons. The optimized approach begins by sorting the strings in descending order of length. This way, we prioritize longer strings, which are less likely to be subsequences of others. Once sorted, we iterate through the array to examine each string. For every string, we check whether it is a subsequence of any subsequent string in the sorted list. If we find a string that is not a subsequence of any other, we immediately return its length. If no such string is found, we return -1. A key observation here is that sorting the strings allows for early termination as soon as the first valid uncommon subsequence is identified, which significantly reduces unnecessary checks. It's also important to note that strings of equal length still need to be compared individually, as their content determines whether one is a subsequence of another. While sorting adds an O, n asterisk log n step, the overall complexity remains O, n squared asterisk L. However, the practical runtime is improved through early termination and reduced comparisons. When evaluating trade-offs, alternative methods like hashing or bit masking come to mind. Hashing can speed up lookups by storing strings and their lengths in a hash table, but it doesn't reduce the overall complexity and increases space usage. Bit masking, on the other hand, allows us to generate all possible subsequences of shorter strings to compare them against longer ones. While this can be effective for small strings, its computational overhead grows exponentially with string length, making it impractical for larger inputs. Ultimately, the sorting and filtering approach strikes the best balance between efficiency, clarity, and ease of implementation. By sorting strings and leveraging the properties of subsequences, we can avoid redundant checks and handle edge cases like duplicate strings or empty arrays effectively. While the worst-case complexity remains O, n squared asterisk L, the practical improvements make it a robust and efficient solution for this problem. To solve the problem of finding the longest uncommon subsequence, we start by sorting the strings in descending order of their lengths. The reason for this is that the longest string, if it is valid, will always give us the maximum possible result, so we can stop our search early. Sorting the array ensures we prioritize longer strings first, which helps in optimizing the algorithm. Next, we define a helper function called is_subsequence to determine if one string is a subsequence of another. This function uses a two-pointer technique, where we traverse both strings and check if the characters of the first string appear sequentially in the second. This approach makes the subsequence check efficient, operating in linear time with respect to the length of the second string. Finally, we iterate over the sorted list of strings to evaluate each one. For every string, we check if it is not a subsequence of any other string in the array. This comparison is done using the is_subsequence function, ensuring that we systematically validate each candidate string. Now, for each string in the sorted list, we proceed to check its relationship with all other strings in the array. If a string is found to be a subsequence of any other string, we mark it as invalid and move on. However, if the string is not a subsequence of any other string, we immediately return its length, as the sorting ensures it is the longest valid uncommon subsequence. To handle edge cases, we include checks for scenarios where no valid uncommon subsequence exists, in which case we return -1. Additionally, we account for duplicate or empty strings in the input. An important optimization insight here is that once we find a valid uncommon subsequence, we can stop further checks, as shorter strings do not need to be considered. This early termination significantly reduces unnecessary computations, especially for larger inputs. By ensuring the input strings are processed in descending order of length, we effectively use a greedy strategy to make the algorithm both correct and efficient. This greedy approach is powerful because it focuses on longer strings first, avoiding redundant checks for shorter ones. Using the two-pointer technique for subsequence verification keeps our comparisons linear in terms of string lengths, which is crucial for efficiency. In terms of data structures, the input is treated as a simple array, which is sorted by length to facilitate the algorithm. Optionally, a set can be used to eliminate duplicates in the input, further simplifying the process. The two pointers in the is_subsequence function streamline the validation of subsequence relationships while keeping the implementation straightforward. For complexity analysis, we note that sorting the array takes O, n asterisk m asterisk log, n, where n is the number of strings and m is the average string length. Subsequence checks, which involve comparing each string with others, contribute O, n squared asterisk m in the worst case. Combining these gives an overall time complexity of O, n asterisk m asterisk log, n, plus n squared asterisk m, which is manageable for moderate-sized inputs. These optimizations ensure the algorithm performs well while maintaining clarity and correctness. Let's walk through an example to see how the algorithm works in practice. Suppose the input array is strs equals ABA, CDC, EA. First, we sort the strings by length in descending order. Here, all strings are of the same length, so the order remains unchanged, ABA, CDC, EA. Next, we start iterating over the strings. For the first string, ABA, we check if it is a subsequence of any other string. Comparing ABA with CDC, we find it is not a subsequence. Similarly, ABA is not a subsequence of EAE. Since ABA is not a subsequence of any other string, we return its length, which is 3. This result reflects the length of the longest uncommon subsequence in the input. The algorithm terminates here because the sorting ensures that no subsequent strings can provide a longer valid result. Thus, the output is 3. Explanation of the code. The provided code solves the problem of finding the longest uncommon subsequence among a list of strings. A subsequence is defined as a sequence that can be derived by removing elements from another string without changing the order of the remaining elements. Here's a detailed explanation. 1. Helper function is underscore subsequence. This function determines if a string S is a subsequence of another string T. It uses an iterator over T and checks if all characters of S appear in T in the correct order. This is done efficiently using the all function and a generator expression. 2. Sorting strings by length. The list of strings strs is sorted in descending order of their lengths. This ensures that we check longer strings first since they are more likely to be uncommon and have the maximum length. 3. Checking for uncommon subsequence. The main loop iterates over each string S in strs. For each string, it checks if S is not a subsequence of any other string in the list. This is achieved using the all function combined with a generator that iterates over all other strings, j equals I. If S is not a subsequence of any other string, its length is returned immediately. 4. Returning the result. If no string is found to be an uncommon subsequence, the function returns -1 is specified in the problem statement. Efficiency. Sorting the strings takes O, n log n, where n is the number of strings. For each string, we compare it against all other strings, leading to a time complexity of O, n squared asterisk k, where k is the average length of the strings. While not the most efficient solution for very large inputs, this approach is clear and addresses the problem requirements effectively. Here, we start with the Java implementation of the solution. First, we define a helper function called isSubsequence, which checks if one string, S, is a subsequence of another string, T. The logic uses 2 pointers, I for the string S and J for T. We iterate through T, and every time we find a matching character for S, I, we increment the I pointer. If we can traverse all of S within T, then S is a subsequence of T, and the function returns true. Otherwise, it returns false. Next, in the findLength method, we sort the input array strs in descending order of string length. Sorting ensures that we check longer strings first, as they have the highest chance of being uncommon. Then, for each string in the array, we assume it might be uncommon and set a boolean is uncommon to true. We compare the current string with every other string in the array. If the current string is found to be a subsequence of another string, we set is uncommon to false and break out of the inner loop. If the is uncommon flag remains true after the inner loop, it means the current string is not a subsequence of any other string in the array. In this case, we return its length as the longest uncommon subsequence length. If no such string is found after checking all the strings, we return -1 to indicate that there is no uncommon subsequence. Finally, the main method is provided to test the implementation with example test cases. For the first test case, the array ABA, CDC, EA includes ABA as the longest uncommon subsequence, so the output is 3. In the second test case, AAA, AA, no string is uncommon, so the output is -1. This demonstrates how the algorithm correctly identifies uncommon subsequences or determines their absence. To solve the longest uncommon subsequence 2 problem, let's take a look at the first example where the input strings are ABA, CDC, and AE. The first step is to sort these strings by their length in descending order. However, in this case, all strings are of equal length, so the order remains unchanged. Next, we iterate over each string to determine if it is a subsequence of any other string in the list. Starting with the string ABA, we compare it against CDC to check if ABA is a subsequence of CDC. This involves verifying if all characters in ABA appear in CDC in the same relative order. The result here is false. Then, we compare ABA with EAE and find that it is not a subsequence of EAE either. This means ABA is not a subsequence of any other string in the list so far. Since ABA is not a subsequence of any other string in the list, we conclude that it is a unique string with the longest uncommon subsequence. Therefore, we return the length of ABA, which is 3. This gives us the final output for this example as 3. Now, let's proceed to the second example, where we have the input strings AB, AB, and ABC. The first step is to sort these strings by their length in descending order. After sorting, the order remains the same, AB, AB, and ABC. With the strings sorted, we now begin iterating over each string to check if it is a subsequence of any other string. Starting with AB, we compare it against AB to check if AB is a subsequence of AB. Here, the result is false, as AB contains characters that do not appear in AB. Next, we compare AB with ABC and find that it is also not a subsequence of ABC. Since AB is not a subsequence of any other string, we determine that it is the longest uncommon subsequence. The length of AB is 6, so we return 6 as the result. This gives us the output for this example as 6. In the third example, the input strings are ABC, ABC, and ABC. Once again, we start by sorting these strings by their length in descending order. Since all strings are of equal length, no changes are made to the order. Now, we iterate over each string to check if it is a subsequence of any other string in the list. For the first ABC, we compare it against the second ABC and find that it is a subsequence. Since we've identified that this string is not unique, we move on to the next string in the list. For the second ABC, the same comparison holds true, it is a subsequence of the first or third ABC. Finally, for the third ABC, we observe the same result again, as it is also a subsequence of one of the other strings. Since all strings in the list are subsequences of others and none are unique, there is no valid longest uncommon subsequence. As a result, we return -1 to indicate this. The output for this example is -1. To analyze the time complexity of our solution, we start with its two main components, sorting the strings by length and checking if one string is a subsequence of another. First, the sorting operation arranges the strings in descending order of their lengths. With n strings and an average length of m, this sorting step takes O, and log n, as sorting depends on the number of strings rather than their lengths. Next, we have the subsequence check. The is_subsequence function works by iterating over the characters of the second string, trying to match each character in the first string. Since this process depends on the lengths of the strings involved, it has a time complexity of O, len, t. If the average string length is m, the subsequence check takes O, m, time per comparison. Now, let's consider the outer loop, which iterates over all n strings. For each string, it checks whether the string is not a subsequence of any other string in the array. This involves a nested loop, where the current string is compared to n1 other strings. For each comparison, the is_subsequence function is called, which takes O, m, time. Therefore, the nested comparison step has a worst-case complexity of O, n²*m, as every string may need to be checked against every other string. Combining this with the sorting step, which takes O, and log n, the overall time complexity is dominated by the nested subsequence checks, resulting in a final complexity of O, n²*m. When analyzing the space complexity, we find that the solution is highly efficient. The sorting operation is performed in place, so it does not require any additional memory. For the subsequence check, the is_subsequence function uses an iterator to traverse the second string and matches characters one by one. This process is done in constant space, meaning it uses O1 auxiliary space. Since no additional data structures like hash maps, sets, or arrays are used throughout the solution, the overall space complexity remains O1. This makes the solution very memory efficient. Let's break down the best, average, and worst cases for this solution. In the best case scenario, the longest uncommon subsequence is found early in the sorted array. For example, if the first string is not a subsequence of any other string, the loop terminates early, and the complexity is dominated by the sorting step, which is O(n*log n). In the average case, the loop will need to iterate over multiple strings to find the result, leading to a complexity closer to the worst case. In the worst case, all strings need to be compared against each other, resulting in the full O(n*m) complexity. Comparing this with a naive approach that generates all subsequences, which would take exponential time, the optimized solution avoids this inefficiency by relying on direct comparisons between strings. This reduces the complexity to O(n*m), making it significantly more efficient than the brute force method. To mathematically confirm the overall time complexity, consider the nested loop structure where each string is checked against others for subsequence relationships. This involves n*(n1) comparisons, and each comparison takes O(m) time. Multiplying these, we get n*(n1)*m, which simplifies to O(n*m) in asymptotic terms. The sorting operation, which contributes O(n*log n, is a smaller term and does not affect the overall complexity. Summarizing, the time complexity is O(n*m), and the space complexity is O1. The best case occurs in O(n*log n, while the worst case reaches O(n*m). This solution is not only more efficient than the naive approach but also balances time and space usage effectively. When solving this problem, there are several common mistakes to watch out for. First, failing to handle duplicates in the input array is a frequent error. Remember, duplicate strings cannot qualify as the longest uncommon subsequence because they inherently become subsequences of each other. Ignoring this will produce incorrect results. Next, some confuse the definition of a subsequence with that of a substring. A subsequence allows skipping characters, while a substring requires those characters to be contiguous. Misunderstanding this distinction can lead to improper implementation and invalid results. Lastly, incorrect complexity analysis is another pitfall. While it might seem feasible to compare all pairs of strings in a naive manner, this approach has a time complexity of O(n*k), where k is the average string length. This can quickly become inefficient and lead to timeouts for large inputs. Understanding these mistakes can save time and effort during problem solving. Another common mistake is failing to return the correct value when no valid result exists. The problem explicitly states that you should return -1 if no string qualifies as the longest uncommon subsequence. Overlooking this requirement will result in test case failures. Additionally, edge cases like arrays with a single string or empty input are often neglected. For an array with one string, the result should be the length of that string, as there are no other strings to compare it against. Conversely, for an empty input array, the result should clearly be -1 since there are no strings to evaluate. Failing to account for these scenarios can lead to runtime errors, so it's crucial to handle them explicitly in your implementation. This problem is built around a recurring pattern in string-based questions, determining subsequence relationships. A key strategy for this is to sort the strings by length in descending order. Longer strings are prioritized as potential candidates for the longest uncommon subsequence because they are less likely to be subsequences of shorter strings. To improve efficiency, a helper function can be used to check if one string is a subsequence of another in O(k) time. It's also vital to test edge cases comprehensively, including scenarios with duplicates, strings of varying lengths, single-element arrays, and empty arrays. During interviews, clearly explaining the distinction between subsequences and substrings demonstrates a strong grasp of the problem and can leave a positive impression on interviewers. There are several related problems that can help deepen your understanding of the concepts involved. Problem number 521, longest uncommon subsequence I, is a simpler version of this problem where you only deal with two strings instead of an array. Problem number 392 is subsequence, focuses on checking whether one string is a subsequence of another, which is a fundamental operation in this problem. Another related problem is number 524, longest word in dictionary through deleting, which involves finding the longest string in a dictionary that is a subsequence of a given string. Lastly, while not directly related, problem number 139, word break, shares some conceptual overlap in terms of dealing with substring patterns and dynamic programming techniques. Exploring these problems can provide additional insights and strengthen your problem-solving skills. When tackling this problem, there are a few alternative approaches to consider. The brute force method involves comparing every string with every other string to determine subsequence relationships. While this is straightforward to implement, it has a time complexity of n²*k, making it impractical for larger inputs. A more optimized approach is to sort the strings by length in descending order and then iterate through each string, checking if it is a subsequence of others. This reduces unnecessary comparisons and improves efficiency, though it requires careful implementation of the subsequence checks. Another option is to use hashing with frequency counts to identify and eliminate duplicate strings early. This approach can reduce complexity to n*k, but additional checks are still needed to handle overlapping subsequences correctly. Each method comes with trade-offs, so selecting the right one depends on the constraints and requirements of the specific problem instance. Great job making it through the problem. Today, we learned how to tackle longest uncommon subsequence 2 by focusing on subsequences and optimizing our approach. Remember the importance of edge cases and leveraging sorting to simplify comparisons. Thank you for watching, and don't forget to like and subscribe for more problem-solving insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!